Today we'll be looking at example questions related to forces on charges in magnetic fields. The questions we'll be looking at here will not be the easiest questions, but they should be the questions that you should be getting sort of ready to do once you've got past the easiest ones. And so let's look at this particular question, which involves an electron. Now, so this particular electron goes through perpendicular electric and magnetic fields. And importantly, it goes through undeflected. All right, so that's an important point. The electric field has a particular magnitude, and the magnetic field strength is also given to you. So that should probably not say -3 there. It should really say -3 on top of the -10, like so. And you're asked to find the velocity of the electron, and you're asked to find also the radius of the circle if the electric field is turned off. So let's draw a basic diagram representing this. We've got our electron heading to the right. Now, there is an electric field, and let's just imagine that the positive plate is up here, and the negative plate is down here, meaning that the electric field is going to go down from the positive to the negative. Now, what that then means is that the electron being charged will then have or experience a force from the electric field going up, and so it would make the electron want to go up, sort of thing, in a parabolic arc, based on what we said before. Now, we know it doesn't do that. It goes through undeflected, and the reason for that is because there's also a magnetic field, which we'll draw like so. Now, the magnetic field is into the page, and using a right-hand push rule, because the electrons are negative, the electron going to the right is like a positive charge going to the left. That means this is going to experience a force downward. Now, if the magnetic field had its way and the electric field wasn't there, we know the electron would just go in a circular arc, and that's where part B might lead us to. But right now, neither of them get their way, and we have simply the electron just passing through undeflected. So we want to work out part A, which is the velocity of the electron. We need to rely on the fact that this electron passes through undeflected. That really means ultimately that the force from the electric field must equal the force from the magnetic field. The electric field pushing the electron up must have that force cancelled out by the force of the magnetic field pushing it down. Now, to calculate the electric field force, it's just QE. You can revise how you calculate the force from the electric field. We've talked about that previously. Now, to calculate the force from the magnetic field, the formula for that is QVB. Now, there's QV perpendicular B or QVB sine theta, but in this case, because it is perpendicular, it is just QVB. We can quickly cancel out the Q, giving us V equals E over B. And as we have those numbers, we can just quickly work that out. So E is 8,000 volt per meter. B is 3 times 10 to the -3. So in this case, you're getting an answer of 2.67 times 10 to the 6 meters per second. So that is your answer to part A. The next part asks you for the radius of the circle if the electric field is turned off. Okay, so as we now have the velocity as 2.67 times 10 to the power of 6, remember when a particle that is charged enters a magnetic field only, it undergoes circular motion. How do we calculate the radius of this circle? Well, of course, that basically needs you to let the magnetic force equal the centrifugal force, which means QVB equals mv squared over r. You do a bit of rearranging here, right? You just cancel out the v. And you can quite quickly get that R equals mv over qb. And we can then just use that formula because now we just need to work out the mass of the electron times the velocity of the electron divided by the charge of the electron and the magnetic field strength. Well, the mass of the electron is something you can just quickly look up in your physics data sheet. Okay, so mass and charge of the electron are all things you can look up on your data sheet, and so you can find that it's 9.109 times 10 to the power minus 31. The velocity we just worked out earlier is 2.67 times 10 to the 6, just from our earlier work. You need to then divide by the charge of the electron, which of course is 1.602 times 10 to the power of negative 19. And the magnetic field strength was 3 times 10 to the power of negative 3. So quick calculation there. Gives us an answer of 5.05 times 10 to the negative 3 meters. So that's how you get the radius of the circle. Remember, whenever you're getting a charged particle to go in a circle, it will enter a circular motion where the radius is equal to mv over qb. Generally, you might not be using that formula directly. You might need to show a little bit of working, but how much work you need to show depends a bit on the context of the question. Now let's take a look at this question. So in this particular question, we now still have a charged particle. This charged particle is now a helium nucleus, and the mass is given to us. And we accelerate it firstly through an electric field across a voltage of 1,600 volts. So here's our diagram. You've got electric field plates. It is drawn the wrong way around, actually. So just ignore the fact that these should be positive on the left. So it's repelling from the left. And just ignore the signs here. This is the negative plate. So basically, we're going to have the positive plate to the negative plate, and it's just going to accelerate across a voltage of 1,600 volts. And then once it gets accelerated, it's going to pass through a magnetic field that's perpendicular to the velocity. So it's, in this case, I've drawn it as into the page. And then you've got a magnetic field strength of 0.52 Tesla. The first question is to calculate the radius of curvature, and the second question is to find the period of revolution. Well, A should be quite clear. We know the radius of curvature, because it's a charged particle in a magnetic field, is just equal to mv over qb. We know the m that is given to us. We know we don't know the v yet. We do know the b, and q is easy because a helium nucleus, you can work out that quite easily. So the real question here is the velocity. So the challenge in A, if you like, is to firstly find the velocity of this particle. And that needs you to know your electric field sort of work. See, this particle is here. It's going to be accelerated forward. Okay. Now, as it's accelerated forward, what that means is that it's going to be put through work. The work is going to be from the electric field. Now, the work from the electric field has a formula of QV. And that Q times this V, remember this V here is voltage. All right? So it's the charge times the voltage. But the thing is, the work that the electric field does on this particle will then be going into the kinetic energy of the particle, which of course is half mv squared, where this v, to be clear, is velocity. So in other words, we would equate qv equals half mv squared. And so we can then basically find out the velocity of the particle because we know the mass and we know the charge. Remember, what's a helium nucleus? A helium nucleus is basically made up of 2 protons and 2 neutrons. That's your helium nucleus. So basically then, as a result of that, your charge is going to be 2 times the electron charge. So this Q is going to be 2 times 1.602 times 10 to the negative 19. Your voltage, capital V, is 1,600. The mass of your helium nucleus is given is 6.67 times 10 to the negative 27. Okay. So, of course, we've got the numbers. We can work this out. So V squared would equal 2 times QV over M. And that's 2 times 1.602 times 10 to the negative 19 times 1,600 over N. That gives us an answer of 1.54 times 10 to the 11. So of course, V is the square root of that, which then gives us an answer of 3.92 times 10 to the power 5 meters per second. All right. So having now got a velocity of 3.92 times 10 to the 5 meters per second, we can then basically sub that into this formula here. So let's get rid of that. Now that we've worked out the velocity, the radius is just going to be equal to m, which we know is 6.67 times 10 to the negative 27, times the v, all over q, which is again 2 times 1.602 times 10 to the negative 19, because it's 2 protons, right? A proton is the same charge as an electron, times v. And that gives you an answer of 1.57 times 10 to the negative 2 meters. So basically, you'll end up going through in a radius of 1.52 centimeters, 1.57 centimeters. That's basically the idea. All right. So now, with that information in mind, we're ready to tackle part B. Because part B asks us to calculate the period. Now remember the period, if you're just thinking about it in terms of a circle, the period is how long it takes to go around the circle once. So if you're kind of going around this circle, using the information we've got, the period must equal how long it takes to go around, or the distance, which is the perimeter, and you can think of that as 2 pi r, divided by your velocity. Okay. So we'll just use that formula. So it's 2 pi times r, which we already have worked out, divided by a velocity. And that should give us an answer very easily. Of 2.52 times 10 to the negative 7 seconds. And so that's how you work out the period of a revolution. What we'll be doing now is we'll be taking a look at 2 questions that are a bit more algebraic. So the question here reads quite wordily, but it's quite simple actually in terms of what it wants. It's basically saying, okay, you've got a particle with charge Q. It's traveling at velocity v. It enters a magnetic field B. No numbers here, of course. This particle has mass m, right? That's not really said in the question, but it has mass m. You're going in, it undergoes a circle, and the time it takes to go around once in the circle is given the letter capital T. You want to find that this capital T is equal to 2 pi m over qb, where m is the mass of the particle, q is the charge of the particle, and b is the magnetic field strength. Now, given what we just did with the earlier question, you might have an easier time of understanding how to do this. So remember, the time taken to go around is basically given by the distance divided by the speed. Now the distance is, well, it's a circle, so it's the perimeter, so it's 2 pi r. Now the speed, of course, is just velocity. So it's 2 pi r over v, all right? Now you've got the 2 pi r, which is good, but you've got the 2 pi, you've got the r over v. Now, it may be helpful to remember that to get r, well, why is there this r? This r is the radius of that. Now, you may recall the formula for r that we referred to earlier, which is r equals mv over qb. So if we sub that in directly, then you'll very easily see that the v just cancels, and you'll get what you want, which is 2 pi m over qb. Whoa. Okay. In this next question, we have a particle of mass m and charge q is moving in a circular path in a magnetic field with strength B. So just your very standard setup. Show that its kinetic energy is proportional to the square of the radius. Well, think of what that means. You want to show that the kinetic energy is proportional to the square of the radius. So you've got kinetic energy on one side, you've got the square of the radius on the other, and you want to show that it's proportional. So you want to basically show that the Ke is equal to some constant, which is as yet unknown, times the radius squared. Well, think of what the kinetic energy is. Kinetic energy from our previous work is half mv squared. So with that in mind, then we now need to basically show that it's K times r squared. Well, we need to know what r is. Now, from previous work as well, r must equal mv over qb. So if r is equal to mv over qb, then I guess r squared must equal m squared b squared over q squared b squared. And noting that here we've got mv squared, it might be helpful to find an mv squared here. Okay. So r squared is equal to m squared v squared over q squared b squared. Now, m squared v squared is m times v, and q squared b squared is still q squared b squared. So r squared is mv squared times this, which in other words then means we can then think of mv squared as q squared b squared over m times r squared. And that is the same thing as this. So we're now able to write it's equal to half times q squared b squared over m times r squared. And noting, of course, that Q is a constant, B is a constant, and M is a constant, and half is a constant. This is just going to equal K times R squared, as long as the K here is equal to half times Q squared B squared over M. And that's how you do these questions. Basically, make sure you know your basic formulas, which are Fe equals QE, okay, W equals QV, FB equals QVB. When your FC equals MV squared over R, so you often get R equals MV over QB. Okay. And those are basically your typical formulas that you'll be using in this chapter. So make sure you know how to apply them. And that's basically the key formulas you'll need when you're dealing with charges in electric and magnetic fields.